All right, elementary calc students, in this section, which is Chapter 5, Section 2, we're talking about relative extrema or extrema. And what that means is that we're looking for maximum and minimum values. And I don't mean the maximum or minimum value for the entire function. We're just going to look and see if there are any little hills or any little valleys on a graph of a particular function. And we're going to talk about ways to locate when those hills and valleys occur, and then how to best determine whether the x-coordinate that corresponds to those points is an x-coordinate that corresponds to a maximum or a minimum. So relative maximum and minimum values are y values. And that's something that I feel like often gets lost in this conversation, but I'm going to try to remind you as frequently as I can, as often as I think of it, that if you're asked for a maximum or a minimum value, you're being asked for a y value. If you're asked when does that maximum or minimum occur, the answer to the question when will be answered with an x value. But as far as what is the maximum or minimum, you're going to answer with a y value. And I've already gone through these notes and I've highlighted a couple of things and bracketed a couple of things because we've got 6 pages of notes here for you. Well, maybe like 3 or 4 pages of notes and then a couple pages with example problems. So I'm going to try to keep this short, but I'll make sure to leave these things on the screen so that you can read them. If you want to read this gray box, you can. I know what it says and how to interpret it, but I feel like to a student who's not a math major, maybe, which most business calculus or elementary calculus students are not, a lot of this stuff gets lost. So I highlighted this little segment that says that a function has a relative or local extremum. Extremum is singular. The plural is extrema or extrema. So a function has a relative or local extremum at a particular c value, that's an x-coordinate, if it has either a relative maximum or a relative minimum there. So relative extremum, a relative extremum will be either a maximum or a minimum. And then there's commentary multiple times, or at least mention multiple times through these notes about what happens at the end point of a graph. What if we're only looking at the values from 0 to 800 maybe, as we saw in a problem in the previous section? How am I supposed to make decisions about what's happening at 0 and what's happening at 800? I'll show you a graph where that's addressed. We're not going to harp on it, but you should definitely be aware of it. Let's see. I actually like this first bullet. The intuitive idea that a relative maximum is the greatest value of the function in some region right around that point. Although there may be greater values elsewhere. I think that's a really good way to think of a relative maximum, and then a relative minimum is, as they describe in the next bullet, relative minimum is the bottom of a valley, and the relative maximum is a peak, or the top of a hill, as I will often say. And then here's another mention about disagreement about calling endpoints maximums or minimums. We're going to get to a graph where I'll talk about that again. This graph, actually. So some things are pointed out here for you, where at the x values x1 and x2, so on our graph, here's x1 and here's x2, you'll notice that the tangent line, there's a little tangent line segment that's been drawn there, that tangent line has a slope of 0. And that is a characteristic of an extrema. So whether it's a maximum or a minimum, you're going to have a tangent line with a slope of 0. Now at x3, because this point is kind of sharp as opposed to being smooth, like a more of a parabolic kind of a shape, this comes to a sort of a sharp corner. there isn't the function's not differentiable there. We couldn't say the slope of the tangent line where x equals x3 is such and such. There is no distinct tangent line at that point, and yet it's a relative maximum because just to the left of that point at x3 and just to the right of that point, everything else is lower. I mean, you would still say that this is the top of a hill or a peak right there. So that is still a relative maximum. And then here's an example to the right at x4 where your end point is being called a relative minimum. And is it lower than all of the other points that are in the immediate vicinity? Yes. Are there any points to the right of it? Not that we're aware of. Could the domain be extended so that the graph goes farther to the right and we find out maybe later in time that the y value at x4 is not actually a relative minimum? We could find that out, but at least for this slice of time that we're looking at, it looks like the lowest point in the immediate vicinity. So we'll still call that endpoint a relative minimum. The left-hand side of this graph goes left and down forever, so there's no opportunity for a relative minimum or maximum there, because a relative minimum has to be the lowest point in a pretty close neighborhood. A relative maximum has to be the highest point in a particular pretty narrow vicinity, but that's not going to happen anywhere here. For example, this point right here, the stuff that's to the right of it is above it, the stuff to the left of it is below it, so it's not a maximum or a minimum. It's not the top of a hill or the bottom of a valley. So if the graph continues off to the left, just diving down and going left, I don't think we're going to see any more relative maximums or minimums over there. When you're trying to, this bullet here says that when you're trying to determine maximums and minimums, you should look at critical numbers and endpoints. Remember that critical numbers are the x coordinates of points where the first derivative is equal to 0 or the first derivative is undefined. And that works for this graph that we just looked at. The first derivative here, because there's a sharp corner, would be undefined. Here and here, the first derivative will equal 0. M equals 0, it says. I highlighted here, it says that a critical number is a candidate for the location of a relative extremum, but only a candidate. So what that's saying is that you could be given a function, you could take the first derivative, set it equal to 0, get an x value of 3 maybe, and it turns out that x value of 3 does not correspond to a point that is a maximum or a minimum. How is that possible? It's got a horizontal tangent line. I know that because the first derivative equals 0 there. How could that end up not being a maximum or a minimum? Let's see, we're toward the bottom of page 2 there. I want to answer that question right away. Here's the answer. At this point where x equals c, you can see that there's a point above it, and the slope of the tangent line to the left of it is positive, so the function's increasing there, and to the right of it, our function continues increasing. So even though the first derivative here, the slope of the tangent line, is actually 0, it's strange, but there's a tangent line that ends up crossing the graph. But the rate of change there is 0, and yet it's neither a maximum nor a minimum. Instead of thinking about it as slopes of tangent lines, the other way you could think of it is, imagine that you're hiking, right? And that's not you probably or anyone that you know, but there's this creature hiking up this incline, and they're going uphill, 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 and they come to a little flat spot where they take a short rest, and then they keep walking and they're still going uphill. So it wasn't that they reached the top of a hill or the bottom of a valley, they just hit this very brief flat spot and then kept going uphill. And then on the return trip, they're coming down, decreasing, decreasing, little flat spot here, and then decreasing, decreasing. So even though the first derivative when x equals c is equal to 0, even though it does technically have a horizontal tangent line, it's not a maximum or a minimum. A little bit confusing, so that's something that we're going to have to watch out for, and we'll work a problem where we have to watch out for that. Here we were, and now here we are. So there's a first derivative test. Critical numbers possible to right, we're going to figure that out. And here's the first derivative test in action. You see in red at the top of that hill it says relative maximum. How do I know that it's a relative maximum? For starters, I can see that the slope of the tangent line right there is equal to 0, which makes it a candidate. Maybe it's a relative max or min. The fact that my function is increasing to the left of that point and decreasing to the right of that point, you can imagine that if you're walking up a hill and then you hit a flat spot and then you start going down the hill, or start going down, a transition from increasing to decreasing would tend to constitute that you had just kind of maxed out. So that indicates the top of a hill. If your function is decreasing and then hits a flat spot and then becomes increasing, that transition from going downhill to uphill means that you have just passed through a valley. And since there is a point down there at the bottom of the valley that has a horizontal tangent line, in other words, the first derivative is equal to 0, that point gets classified as a relative minimum because, again, we transitioned from decreasing to increasing. That's the first derivative test. That bullet says what we just said. Second bullet says what we just said. Third bullet says, now we're going to define what we just said in mathematical talk using all these functions and variables and constant values a, b, and c, and say very specifically and clinically what we were just talking about by circling things and talking about going uphill and downhill. So you're welcome to read this, but it says what we were just talking about. And there it was, 3 pages of notes, and now we're into example problems, which is great. So this first example is showing us a graph that we've actually seen just recently in the previous section, and immediately we're reminded that this is not the graph of f of x, this is the graph of f prime of x. So all of these are x values, and all of these that look like y values are actually slope values or rate of change values. So let me ask you this. When x equals negative 2.5, is our function increasing or decreasing? Again, look at this graph and tell me, when x equals negative 2.5, is our function f of x increasing or decreasing? So see what you think, and now let's talk about it. At negative 2.5, I'm looking up here at this point, maybe right here. That point has a y value, so to speak, of approximately 1.5. That number 1.5 is the slope of the tangent line to the graph f of x at the point where x equals negative 2.5. Since f prime of negative 2.5 equals 1.5, which is greater than 0, I know that my original function is increasing at the point on the original function where x equals negative 2.5. One more time, because the slope of the tangent line there is positive, the function is increasing. The original function, not this function that you're looking at on the screen, this isn't the original function, this is the derivative of the original function. So you've got to be careful there. It's a little mind-bending. I remember struggling with it myself. when I started looking at graphs of derivatives of functions. So you really have to be careful and make that connection between what are these y values that we're seeing on the screen right now really communicating to us. They're not really y values. They're f prime values. They're m values. They're slope of tangent line values. They're rate of change values. Hang with it until you break through and make that connection. It's worth it. Okay, so, well, all of these points up here, this has a positive slope, this has a positive slope, right? All these y values are greater than 0. All those m values are greater than 0. I'm going to even scribble out this y right here. I can't stand it anymore. Let's make it say m, all right? These are slope values, slopes of tangent lines. So it looks like everywhere to the left of -2, our original function has positive sloping tangent lines. And if it has a positive sloping tangent line, it means the function is increasing. So I would say that we're in, let's say, how about on -infinity up to -2, we're increasing. And then if you look at the graph again, where this graph is below the x-axis, all of those y coordinates or m coordinates are negative. That means that on -2 to 2, our original function, which is not graphed here, our original function is decreasing. And then this graph that we do see on this screen transitions to this portion over here where we have m values that are greater than 0 again. We're above the x-axis, therefore on 2 up to positive infinity, those are x values, we are increasing. Our original function is increasing again. So where did the changes happen? It looks like at -2, we transitioned from increasing to decreasing. And at x equals +2, we transitioned from decreasing to increasing. A transition from, I shouldn't draw it like that, from increasing to decreasing. What do you think? Does this look like a maximum or a minimum to you? I'd say when you go from increasing to decreasing, you're looking at a maximum right there, which means that where x equals -2, we have a relative maximum. Increasing to decreasing, therefore, relative max at x equals -2. Ugh. Well, sneak a little negative sign in there. Relative max at x equals -2. And then let's move over here. Here we're going from decreasing, and then we transition to be increasing. That looks like a minimum to me. So, I don't know how that happens. I don't know what it is that I do. And then I have to enable my pen again, and then pick my pen color. Now I'm drawing with my finger. It's so weird. Technology. Relative minimum at x equals +2. So we found our critical values just by looking at changes in the first derivative. Where our first derivative went from positive to negative, we had a relative max, and where it went from negative to positive, we had a relative minimum. So that's sort of a visual application of the first derivative test. Again, when you go from a positive first derivative to a zero derivative to a negative derivative, that constitutes a maximum. Here, the function's not differentiable because it comes to a sharp corner, but that's okay. We're still transitioning from a positive to a negative in terms of what the first derivative is doing. Here's the transition from negative to positive, which means it's a minimum. Here it's transitioning from negative to positive, still a minimum, even though the first derivative is not defined there because it comes to a sharp corner. And then these last two no relative extrema examples we already talked about. So here is a reminder, it's written in blue for you, that values of the extrema are y values. When does the extrema happen? The answer to that question is an x value. What is the extrema? The answer to that is a y value. X value describes when, y value describes what. Okay, find the x values of all points where this function has relative extrema or extrema. Find the value or values of any of the relative extrema that we find. Great. So let's cruise through this. F prime of x. We're going to take our first derivative and set it equal to 0 in order to chop up the number line. So the first derivative is equal to 3x squared minus 12. Oh, that's interesting. Okay. And then we're going to set this equal to 0. And then we'll solve. Adding 12 to both sides, dividing both sides by 3, square rooting both sides. So I found two potential critical numbers, positive and negative 2. Well, they're definitely critical numbers. It's a question of whether or not we're going to have an extrema at both of those points. So now that I have my two critical numbers, you should label those as critical numbers, negative 2 and positive 2. Now I'm going to have a closer look at what's my function really doing in terms of increasing and decreasing and maybe increasing again, that's going to create those peaks and valleys or hills and valleys which will yield relative maxima and relative minima. So I take my number line, I'm going to put negative 2 on there, positive 2 on there, and then we're going to test. I'm going to test an x value less than negative 2, test an x value between negative and positive 2, and test an x value greater than 2. Where am I going to test them? I'm going to test them in my first derivative in order to see if my function is increasing or decreasing on these three intervals. So I think maybe we could stay in here. I'll just zoom in and write small. So let's try f prime of negative 3. Now f prime was 3x squared minus 12. And that is 27 minus 12, which is 15, which is greater than 0, therefore increasing. And then let's try f prime of 0. That's between negative and positive 2. Get the 0 in there. 0 minus 12 is equal to negative 12. Which is less than 0, therefore decreasing. And then let's try f prime of positive 3. That's 27 minus 12 again, which is positive 15 again, which is still greater than 0, which means it's increasing on that interval. When you transition from increasing to decreasing, you're at the top of a little hill, which means there's a relative maximum there. increasing to decreasing, relative max at -2, or x equals -2. When you transition from going downhill to going uphill, you must be at the bottom of a valley, and therefore you have a relative minimum, and this time at x equals +2. Let's check in on the question again. Find the let's zoom out. Find the x values of all points where the function has relative extrema. We have done that, -2 and +2. And now we're going to come up here and find the values of those relative extrema. So I have a relative max that happens when x equals -2. How do I find the actual relative max? What is, I should say, the relative max? Don't forget that the answer to that question is a y value. How do I find the y value? I take my x value of -2 and I plug it into my original function. I want a legitimate y value, not an m value, not a slope of a tangent line when x equals -2. I already know what that is. It's 0. Now I want the actual relative maximum y coordinate. So relative max of f of -2, which equals -2 to the third power minus 12 times -2 plus 2. That is -8 plus 24, which is 16 plus 2 makes 18. So we have a max of 18. And we have a minimum of f of +2, which is 2 to the third minus 12 times 2 plus 2, which is 8 minus 24, which is -16, plus 2, which is -14. So you have a relative max of 18 when x equals -2, and you have a relative minimum of -14 when x equals +2. The critical points are -2, 18 and +2, -14, x, y. Those are your critical points. Your critical numbers are -2 and +2. Your relative maximum is 18. The relative max is just the y value. The relative min is just -14. So some slight differences depending on what question is being asked. So making sure that you know the distinction between the questions will help you to answer correctly. Here the instructions are the same, but the function is different, and we have a limitation on our x values because the logarithms and natural logs can only accept positive values as input values. So because our function here works with the natural log, input values must be strictly greater than 0. Let's take the first derivative. First derivative of the natural log function. You haven't done a lot of these yet, so you might not remember, but it's 1 over x minus the derivative of x is 1. And then we're going to take that and set it equal to 0. Add 1 to both sides. Multiply both sides by x. And you have your critical number. Now, is that critical number corresponding to a relative maximum or a relative minimum? You'll have to take the number line and put the number 1 on it and test over here and test over here. And when I say test, I mean testing x values in the first derivative. So test in the first derivative. Plug in a value of Should you plug in an x value of 0? Probably not, because 0 is not even in the domain of the original function. So you have to plug in something that's between 0 and 1. So maybe plug in 1/2. That'll return a positive f prime value for you. F prime of 1/2 is greater than 0. F prime of maybe 2, that's a number that's greater than 1. And that's going to give you an output value that's less than 0. So if your first derivative is greater than 0, then it's increasing. If your first derivative is less than 0, then it's decreasing. If you're transitioning from increasing to decreasing, you must be at the top of a hill. So you have a maximum at x equals 1. What is that maximum value? I'll leave it up to you to take x equals 1 and plug it back into your original function. I'll give you a hint, the answer is negative. And then finally, there's a maximum profit application problem. I'm not going to do this whole thing, but I will tell you. I say that I'm not going to do the whole thing, and then sometimes I just can't help myself. But let's see. So we've got a revenue and a cost function for the manufacturer of grandfather clocks, where x denotes the number of clocks made. What is the maximum annual profit? So you're looking for the maximum annual profit. I don't see a profit function, so you need to design a profit function. P of x equals profit equals revenue minus cost. Then you're going to need P prime of x equals, and then you'll have to take P prime of x and let it be 0. And then you'll have to solve. And when you solve it, you're going to get an answer of x equals something. That's how many clocks have to be manufactured in order to generate the maximum annual profit. You'll have to take that x value and plug it back into your profit function in order to answer the question, what is the maximum annual profit? So there you go. There are instructions to complete that type of a problem. You will undoubtedly run into a couple of those style of word problems as you're going along through this chapter. So that should take you where you want to go. It's a template. It's a rhythm. These types of problems where you're looking for maximums and minimums, there's a rhythm to them. So try to keep that big picture of the process in mind, like what I just talked through for this last example problem. I think that if you can internalize that pretty well in order to have a good feel for the flow of these types of problems, that'll be beneficial. And then also maintaining that relationship in your mind between the graphs of an original function and its derivative function. Remembering that if you're looking at the graph of a derivative, that the y values actually represent m values, or slopes of tangent lines, and that if it's positive, it's increasing, if it's negative, it's decreasing. And then the transition from increasing to decreasing means you're at the top of a hill. If you're decreasing to increasing, you're at the bottom of a valley. That was pretty much the whole section in about 60 seconds. But, you've got to parse through all of that stuff and get yourself a little bit of practice. So head off to do some homework, keep practicing, be patient with yourself, ask questions, whether it's of me or your professor or a tutor or a friend who actually knows what they're doing and is a decent tutor or teacher, and I'll see you in the next section. Thanks so much.